Okay, let's begin. So on the tutorial day we saw what Boolean algebras are. Yeah, we got a glimpse of what Boolean algebras are. So let us start with the theory behind that. So we say that a lattice is bounded if it has a minimum which we denote by 0 and a maximum which we denote by 1. So we write L meet join 0 1 for a bounded lattice to emphasize on the bounds. If x in L is a if x is an element of a bounded lattice, then we say that it is complemented if there exists some other element y such that x meet y is equal to 0 and x join y is equal to 1. So basically, I mean, think about the diagram, what it's trying to show. Yeah, I mean, this is my 1. I mean, usually that's how we draw lattice. Yeah, it has a spread. Then x is an element here. So x and y, their meet, which means the greatest lower bound is 0. So there is nothing common below x and y except for the lowest element which has to be below them, and there is nothing common above x and y. So they are like maximally apart. Yeah, so that's why it's called a complement. However, we saw that in M3, yeah, you remember M3? In M3, one element can have multiple complements. B is a complement of A, C is a complement of A, so there are multiple complements. But we are going to rectify that if we put this condition that the lattice is distributive, the bounded lattice is distributive. So let x be any element, then we'll prove that x has at most one complement. So for a proof, what should we start with? Suppose for a contradiction, I mean, I don't even need to say suppose for contradiction. Suppose y and z are two complements for x. Okay, one thing we should know about the top element and the bottom element is that x is equal to, oh sorry, not x but y. Y can be written as y meet 1. What is the greatest lower bound of y and 1? Y. Okay, so y is equal to y meet 1. What can we write for 1? Well, we have to introduce z in this. So x join z is 1. So therefore y meet x join z, then we will use distributivity. Let's do that. So that's y meet x join y meet z. What is y meet x? 0. Y meet x is 0. So 0 join y meet z, which is equal to y meet z. So see what we proved, that y is equal to y meet z. Similarly, by exchanging roles of y and z, by swapping y and z, we get z is equal to y meet z. I mean by commutativity, z is equal to z meet y, but by commutativity it's y meet z, and hence y is equal to z. Done. Very simple proof that every element in a distributive bounded lattice has at most one complement. However, we saw that in a 5-element lattice, in any 5-element lattice, not all elements have complements. Right? So let me write it as a definition. So say that a bounded lattice is complemented if each element has a complement. So every element has a complement. Yeah, this is a very strong condition. And in particular, if we assume that our bounded lattice happens to be distributive, then distributive bounded complemented lattice is a Boolean algebra. So definition: a Boolean algebra is a bounded distributive complemented okay, this was a mess, don't know why. Bounded distributive complemented lattice. So basically, okay, let us look at the definition. It is bounded because then only we can define complements. It is distributive, so every element can have at most one complement, and it is complemented, so every element must have at least one complement. So therefore, overall there is exactly one complement. For every element there is exactly one complement. So denote the complement, the unique complement of X in L by negation X. Okay, negation is this particular sign, negation X. So negation is actually a function. It's a function from L to L. So negation is a function. Actually, I mean, let me change this. So X in B. Yeah, our tradition is that for a poset we write P, for a lattice we write L, for a Boolean algebra we should write B. Okay. So negation, in fact, neg from B to B is a function. Okay, so how do we write the signature of a Boolean algebra? For a lattice, the signature is L meet join. For a bounded lattice, the signature is L meet join 0 1. For a Boolean algebra, the signature would be okay. So this is B equal to B meet join negation 0 1. Okay, here this refers to the Boolean algebra and this refers to the underlying set. I mean, a Boolean algebra is a set B with these operations. So meet and join are binary operations, negation is a unary operation, and 0 and 1 are zero-ary operations or constants. Okay, so this is what our Boolean algebra is. So this is named after George Boole. Okay, so there is something I want to talk about. So George Boole is the name of the mathematician who invented these things, but please observe this particular B over here. It's written small and not capitalized. That goes against our intuition, right? Whenever the name of a person is involved, then we write their name first letter of that name is capitalized. However, very few mathematicians and physicists have this honor that their name is so important, their work is so important that their name is not capitalized anymore. It has become a word in the dictionary. Okay, maybe you have learnt about Abelian groups. Yes, Abel is also written with a small a. Okay, there are very few people who have got this honor. So George Boole is definitely one of them. Without Boolean algebras, computers cannot exist. And what is the reason behind that? So let us look at the first example. First example is that of b equal to 0, 1. Or as we will see in logic, we will also call them false and true. These are the logical truth values. So this is the two element Boolean algebra. What is the meet operation here? The table for meet, I am sure you can complete this. Tell me, T meet T is? T meet F, F meet T, and F meet F. Very good. Join. T join T, T join F, then this one is also T and this one is F. Then what is negation? T and F. Negation of T is F, negation of F is T. Okay, so 0 and 1 can also be used to denote this. So this is the two element Boolean algebra. Oh yes, I am just going to write BA for Boolean algebras, yeah, as a short form. Whenever we can, we denote it by this 2. It's a bold 2. Okay, because we want to distinguish. See how we distinguish between this B and this B. This B is just the set, and this is the corresponding algebra structure. So we will denote this by 2. One more thing I should add, yeah, to a Boolean algebra definition, please add that. Yeah, assume 0 is not equal to 1. Yeah, otherwise there are some problems. We don't want a singleton Boolean algebra. Everything becomes trivial there. Okay. So this is the two element Boolean algebra. So now we know that there exists a two element Boolean algebra. What about a three element Boolean algebra? Can you tell me all three element bounded lattices? 0, A1. There is only one possibility, yeah? So is that a Boolean algebra? 0, A1, three element Boolean algebra. What will be, what is the complement of 0? Complement of 1? Obviously. What's the complement of A? Does not exist. We also saw that day that 5 element Boolean algebras do not satisfy, they are not complemented. Every 5 element Boolean algebra had one element which did not have a complement. What about 4?
Not for chain but for the other one.
Yeah, not for the chain.
Not for chain but for other one, yeah, M2. M2 is a Boolean algebra. Yeah, so basically an element and its complement, as long as it is non-zero and non-one, element and complement, they should be incomparable with each other. So we definitely have a 4 element Boolean algebra. I am just going to draw it. 1, 0, A and negation A. Okay, this is the 4-element Boolean algebra. There cannot exist any other 4-element Boolean algebra. Yeah, just this one. Then what cardinality do you think the next Boolean algebra will appear?
6.
In 6 it doesn't appear. It will be, the next thing will be 8. So now can you tell me what all cardinalities Boolean algebras can appear? 2 to the power n. And what is 2 to the power n? It is the cardinality of the power set. So let us write down our general example, power set of x with what is the meet? Intersection. Join is union. Then what is negation? Complement. I am writing it as complement, but it is x minus blank function. Then what is 0 and 1?
How are you defining complement here?
Complement is with respect to x. Yeah, x is our universe in that case. So this is a Boolean algebra. So I mean, if you choose x to be singleton, then power set of x is 2-element Boolean algebra. If x happens to be 2-element set, then power set is 4-element, and so on and so forth. Yeah, the next one, let me draw it. So empty, then singleton 0, singleton 1, singleton 2, then here I will write 0 1, then 0 2, then 1 2 and 0 1 2. Yeah, this is the Hasse diagram for this. This is our 8-element Boolean algebra. It is simply the power set of 3-element set. Okay, can you think of any other example of a Boolean algebra? Okay, so let me give you a fourth example. I am going to take a sub-algebra of the power set Boolean algebra where PFC of x is the set of all finite or cofinite subsets. Okay, what is the meaning of finite? You understand. Cofinite means the complement is finite. Okay, so cofinite means, so y is cofinite. If x minus y is finite. So please check, yeah, in your mind that intersection of any two finite sets is again finite, union of finite sets is finite, complement of finite is cofinite. Similarly, union of two cofinite is cofinite, intersection of two cofinite is cofinite again, yes, and intersection of a finite and a cofinite. Yeah, cofinites are close to the top, finite are close to the bottom. Yeah, we are removing the middle portion of all those subsets which are infinite and their complements are also infinite. Okay, so please verify that this is actually a Boolean algebra. Okay, there are some basic properties. There will be a fifth example and I am just going to write the name for now. There will be a countable atomless Boolean algebra. In logic. Okay, when we study the logic part, then you will see this example. I am going to postpone it until then. So some basic properties of Boolean algebras, let me mention them. Some basic properties. What will be x join 0, and this is also x meet 1. Yeah, we already used this. Then what is x meet 0 and x join 1? Oh, okay. Then we also have De Moivre's law. What does it say? State negation of x meet y is negation x join negation y. Yeah, please verify this for yourself. And the other property is the dual property, that negation of x join y is negation x meet negation y. Okay, so these are called as De Moivre's law. De Morgan's law. De Morgan's laws. I don't know why I am thinking about complex numbers. Okay, De Morgan's laws. Then we also have some other properties. Yes, fourth property. I mean, we can, because it's a lattice, we can define less equal. When is x less equal y? If x meet y is, or x join y is y. Okay, good. So x is less equal y if and only if negation y is less equal negation x. Yeah, so negation is actually order reversing. Okay, then another property, that less equal is a congruence relation. So what is the meaning of congruence? That whenever, if x is less equal y and a is less equal b, then x meet a is less equal y meet b, and x join a is less equal y join b. If I have two inequalities, I can take their meets and I can take their joins. Okay. So all these properties I am leaving as homework. Please prove them. Yeah, these are really basic. And you can do that. Okay. Then there is one property which I will prove here, that is the sixth one, that x is less equal y, x is less equal negation y if and only if x meet y is equal to 0. Okay, this is a very crucial property of Boolean algebras, that you can compare an element with negation of another element in this way, if and only if, so x lies below negation y, if and only if x meet y is 0. Yeah, it's intuitive if you think about diagrams. Yeah, so let us try to prove it now. So suppose x is less equal negation y, then I can use property number 5 for the identity y less equal y. Okay, then what will I get? X meet y is less equal negation y meet y. What is negation meet y? Negation y meet y? 0. So therefore, now x meet y, it is less equal the minimum element. So it has to be 0. Simple proof. Okay. Conversely, suppose x meet y is equal to 0. Then how do we prove the other side? Any ideas? Think. We need to prove that x is less equal negation y, which means x meet negation y is tell me what to do. Sometimes I feel I am spoon feeding you a lot of information, so you don't think.
Take the join of x join complement by both sides.
X join
Complement by both sides.
x join complement y both sides.
Yeah, join. Take the join.
Join of this, okay. Then x join this is equal to 0 join this. Then what happens here?
With join with x meet join y.
X meet negation y. Is there any problem with this? See, let us open this bracket. So x join negation y and y join negation y. What is this side? What is y join negation y? 1. So what is 1 meet anything? Itself. So therefore this is this, and that's equal to what is the other side? 0 join negation y. Done. Yeah, this is the restatement of x is less equal negation y. Yeah, you have to play around with these identities. Yeah, and it's also interesting. Okay, any problems so far? These are some of the basic properties of Boolean algebra. Okay, so our next goal is to show that there cannot exist any finite Boolean algebra which is not in this list 3. Yeah, I mean intuitively you understand that all Boolean algebras must finite Boolean algebras must contain 2 to the n many elements for some n bigger equal 1. But we need to prove it. Okay, so for that let us find out. So given a finite Boolean algebra, we would like to figure out what is it the power set of. Correct? It should be a power set of something x. How do you figure out x? Now look at these pictures, the 8 element Boolean algebra. Look at how do you obtain the elements back. In that picture, where are the elements? The elements of x?
Above the empty set and
Above the empty set. Yeah, all of them are singletons. Now, if in this picture I remove this part, then what are these singleton 0, singleton 1, singleton 2 in order theory language? What are they? Minimal elements. Yeah, not minimum, minimal elements. So we are precisely going to do that. So say that A in B is an atom. Atom is something which is unbreakable. 0 means doesn't exist. Yeah, atom is something unbreakable. There is nothing smaller than that. Is an atom if A is not equal to 0 and for all B less equal A, B is equal to 0 or B is equal to A. In other words, atom is a non-zero minimal element. An atom is a minimal non-zero element. What is an atom in the two element Boolean algebra? 0, 1? 1 is the atom. Okay. Then in this example, A and negation A are atoms. In this example, singleton 0, singleton 1, singleton 2 are atoms. And now again look at this. Countable atomless Boolean algebra. So some Boolean algebra where there are no atoms. Okay, so that we'll see later. So say that B is atomic if for all x in B, x not equal to 0 implies that there exists A in atoms of B such that A is less equal x. Yeah, here atom of B is the set of atoms of B. So it's similar to complement and complemented. An element has a complement, and complemented means every element has a complement. Here we are saying some element is an atom, and then the Boolean algebra is atomic, which means every non-zero element lies above an atom. So let me go back to the slide of examples. Yeah, then we'll see something. So what about 0, 1? Is it above some atoms? Yes, so which atoms are lying below it? Singleton 0, singleton 1. Yeah, be careful what you say. Then 0, 1, 2. What are the atoms below 0, 1, 2? All three singletons. In fact, are you observing some pattern here? That for 0, 1, what are the atoms below it? Precisely the singleton subsets of that. And moreover, if I know all the atoms below 0, 1, then I can reconstruct 0, 1 by taking, in this case union, but in general join. Okay, that will be the proof of our representation theorem. Exactly that. Stone's representation theorem. Marshall Stone is the name of the mathematician who gave this proof first time, that every finite Boolean algebra is isomorphic to a power set Boolean algebra. Okay, so that's our representation theorem. We are working towards that. the first thing that we proved was, we proved this property 6 that will be used. Now we have given the definition of an atom, so that at the set of atoms of B will serve as our set X, for constructing the power set. Okay. Now there is another thing which I should prove. And that is, suppose B is a finite Boolean algebra then B is atomic. Okay, what's the meaning of atomic? That every element, every non-zero element is above an atom. How will you prove that? Think about it. If I am given a non-zero element X, how do I prove that it is above an atom? See, this proof is no different than just asking that every finite poset has minimal elements. So what do I do? I'm not going to write a proof, but I'm just going to give you an idea. So consider the finite poset B minus singleton 0. Singleton 0 means remove the minimal element, and argue that it must have a minimal element below any element. You start with any element. I will tell you the rough sketch of the proof. You start with any element. Is it minimal? If yes, then you are happy. If not, then there is something below it. Again, for that element you ask, is it minimal? If yes, you got what you wanted. If not, then you obtain a further strict lower bound. And then you cannot obtain an infinite chain because our poset is finite. That's all. Okay. So one more ingredient that we need to state Stone's representation theorem is the word isomorphism. We haven't yet defined it. Because every finite Boolean algebra is isomorphic to a power set Boolean algebra. We haven't defined isomorphism, but before isomorphism we always define a homomorphism. Right. And then an isomorphism would be a bijective homomorphism. Very good. All of you are smart now. So given Boolean algebras B and B prime, say that a function h from B to B prime is a Boolean algebra homomorphism, BAHM. If, tell me what should I write? All of you know the definitions. What should H preserve? Join, meet, complement, 0 and 1. Okay, but I am going to write a shortcut. If for all x and y in B, h of x meet y is equal to h of x meet h of y, and h of negation x is equal to negation of hx. That's all, full stop. Why did I not write 0? H of 0 is equal to 0.
So we can take exponent follow from
It will follow from this. Okay, so just this is the definition. Yeah, and then Boolean algebra homomorphism, and H is a Boolean algebra isomorphism if H is a homomorphism and is bijective. It's a bijective homomorphism, then it is called an isomorphism. Okay, so we will show that a Boolean algebra homomorphism preserves 0, 1 and join. Okay, h of 0 is equal to h of x meet negation x for any x. Okay, then meet is preserved, so therefore h of x meet h of negation x, but negation is also preserved, so that is h of x meet negation of h of x. So please be warned, yeah, I mean whenever we write this, then the first meet is in B, the second meet is in B prime, and similarly for complements. So h of x meet negation of hx, what should it be? 0. So done. What is h of 1? It is h of negation of 0. So therefore negation of h of 0, but h of 0 is 0, we just proved that. So negation 0, that is equal to 1. Simple. What is h of x join y? Well, join negation is, maybe I can add that property. Yeah, that also you should prove. Double negation of x is x. Right, you take negation twice. Yeah, please try to prove that. Yeah, that follows from uniqueness of complement. So negation x is a complement of x, then x is the only element which can be the complement of negation x. Okay, so now look at De Morgan's laws. How can I write x join y? Complement of complement, yeah. So this is complement of, and please continue. Yeah, I am not going to finish this. Yeah, it's easy, you just follow the definition. Okay, so far so good. We have seen the definition of a Boolean algebra homomorphism and an isomorphism, and it's simplified, yeah, because we just say meets and complements are preserved, they determine everything else. Okay, now comes an interesting fact which you will prove in the tutorial. So given Boolean algebras B and B prime, a function h, I will always use h here, a function h from B to B prime is a Boolean algebra isomorphism if and only if H is an order isomorphism. Yeah, when I am talking about an order isomorphism, I simply mean this: B less equal to B dash less equal. Okay, can you remind me what is an order isomorphism? It preserves and reflects orders, and it is bijective or surjective equivalently? Yeah, it's an order isomorphism, which means it is an order embedding and it is surjective. Understood? So, see, such a beautiful connection. We don't really need to look at preservation of meets and joins and complements. You only have to preserve the order. Okay, the order is sufficient to determine. Why? Because everything else follows from the order. The equivalence between algebraic and order theoretic definition of a lattice. Yes, what did we say? That meets are GLBs and joins are LUBs. So meets and joins are preserved if this is an order embedding and surjective order embedding. Then meets and joins are preserved and complements are preserved. You can prove this. Yeah, so this is a tutorial problem. Okay, so now we are ready to state Stone's representation theorem for finite Boolean algebras. Suppose B is a finite Boolean algebra, then B is isomorphic to a power set Boolean algebra for some finite set X. Okay, it is a Boolean algebra isomorphism. Okay, so first thing, since B is finite, B is atomic. We argued that every non-zero element has an atom below it, correct? So since B is finite, B is atomic. So let ATB denote the set of its atoms. The set of atoms of B. Okay, then we need to define H from B to some power set. Which power set will we choose? Power set of the set of atoms. By, if I take an element X, then I will map it to all the atoms which lie below X. And how do I write that? I am going to use this notation. What is D? Down set of X. So all the elements which lie below it and are atoms. Yeah, that's my definition of H. Okay, what do we need to show? I'm going to call this property star. By star, it suffices to show that H preserves and reflects order and H is surjective. Understood? H preserves order, H reflects order. So what is the order? So in other words, we'll show that. So we will show If x is less equal y, then x is less equal y if and only if hx is contained inside hy. Okay, because the order on the right hand side in the power set, the order is containment, and that we will do on the next day. It's an easy proof from here. Let's stop for now.